Shh. We need to get started. We don't have enough time to talk now. All right, here's your first example. Example 1. Is everybody there? All right, we're solving equations with complex numbers. Change that 7 to a y. This needs to be a y there for this to work correctly. Uh-huh. Okay. You've never done this before, but it's not very hard. Here's a plus bi form for complex numbers. So if we want to solve an equation, we need to make sure both sides we recognize what is the real part and which part is the complex or imaginary part. So here's the a part. See how we have this plus 3i, so 3 is the b. This is the real part, this is the imaginary part. 3 is the b. Now over here, it changes a little bit here because we've got an I here in 2 places. So we need to factor the I out so we can see what B is. And put the I in front, or excuse me, to the right like it would be if it was in A plus BI form. This is like your A plus B is the parentheses I.
It's just the 3B or the whole 3I?
No, just the 3. Look. The number in front of I is B. So the first thing you have to do is make sure you understand you have 2 complex numbers in A plus BI form. Now we can solve because if these 2 complex numbers are equal, then their parts have to be. Just that would be understood. So that means this A has to equal this A. So you take 2x plus y has to equal 9. Those are the real parts. See where I got that? Now we're going to set the b's equal. Over here, b is 3, right? This is your b on this side. B over here, b here. So now, what's our b equal here? 3. Now I'm going to put the 3 over here so it's in standard form. So you have x minus y equals 3. So the way you understand this is you set the real parts equal, then you set the imaginary parts equal. The ones with the i's. Now what do we have here from algebra? We have a system.
Yeah.
Remember substitution, elimination, those type of things? This one's set up for one right away. What's it set up for? No. You could do substitution, but yes, isn't elimination right? Aren't the y's going to be eliminated if we add them? Remember elimination, you want one opposite and one and both alike. So when we add these, we get 3x equals 12. Right? And we got x is 4. Yes. This is a system of equations. That's what we got here. That's how you solve it now, but we're not finished. We need the y. So where do we go to get the y? Yes? Now you can put it in either one. You can put it here, second one for x. So you'd have 4 minus y equals 3. Solve that equation, you got your y. Subtract 4, we got negative y equals negative 1. Divide by negative 1. Should be a positive, shouldn't it? And now we have our 2 answers. Do the next one for bonus, please. concept is still the same. Still doing the same thing. You don't have to do anything to the right side. It's in a plus bi form already. How come you're not writing anything? How come you're not writing anything?
I got it.
Okay. It's all right. That's why we do this, so you can get unconfused. Well, our goal is to solve for x and y. But we have i's in this. We have imaginary numbers, which makes it complex. So you have to get each side set up so it's in a plus bi form, where you have an a plus bi. This one's already that way. So this is your a, right? And this is your b. Over here, you've got to determine what's my a and b. Your a doesn't have an I on it, does it? There's no I on it. That's how you know what your a is. And say that again. Yes, this is your a right there. There's no i's there, are there? But your b, you have to factor the I out. So what's your b going to be here? Yes. Your b is what's times the I. See, b is times the I. Whatever's not with the b is your a. That's imaginary, and this is the real. So you set the two parts equal. Yeah, I'm recording a lesson here. So. All right. Has anybody got an answer yet? Got an answer? What'd you get, Luke? X equals 1. What'd you get for y? Haven't got y yet. What'd you get for y? Well, let's see if that's right. So what do we set equal to get our two equations? Yeah, our a here is 2x plus y. There's no i's with this. There's no i's with this. So we set these two equal to each other. Now, what's our b on this side? X plus y. What's our b on this side?
4.
See, aren't they both with the i's? That's how you know to set those equal. Everybody see where it comes from? Sometimes you have to change it to get in the right form. Sometimes you don't. In this case, you had to. Now, this is not ready for elimination, but how would you change this to make it ready real quick? Very good. Multiply the bottom one by -1. But whatever you do, you have to do to everything, don't you? Isn't that the same as just changing everything to its opposite? And that's how Matt got x equals 1. Because when we add now, 2x minus x would just be x, right? This is gone, eliminated. That's why they call it elimination. Equals 1. You can put 1 back in for x up the top one if you want. 2 times 1 is 2 plus y equals 5. Oops. Anybody get 3? Okay. So we'd subtract 2. Where are you talking about? Yes. You all forgotten your algebra completely?
Yes. No, I'm just. Yes.
That's what this is solving systems. It should have done in Algebra 2 and in Algebra 1. Well, it's algebra. You're supposed to remember what you learned. Some of you have a habit of thinking, I don't need this anymore. I'm just going to remember it long enough for the test. All right. Yes, we added these because in elimination you add and one of the variables disappears. See, the point was to get one of them opposite and alike, so that happens. So when one of them's gone, we can figure out the other one. Then you just substitute back in. Did anybody finish this and get 1 and 3? All right, I'll give you a bonus point for 1. You get 2 if you got both. All right. Let's go to the next problem. Yes? Okay, here we go. Absolute value of a complex number. This is also review, but you'll see this is very familiar. If I want to find the absolute value of a plus bi, that equals something you've been doing for the last month. Doesn't that look familiar?
Yes.
Don't just say that just to say that. When have we done this before?
Last 10 sections.
The R.
Thank you. Thank you. Junior high. All right. Yeah, we had r squared equals x squared plus y squared, and we take the square root, right, to find the r, which you're going to do here in a little bit again. This has the same relationship. So if I want to find the absolute value of, let's do a there, 3 minus 5i. It's very simple. It would be the square root of what? That there's no i's over there. Are there? I just picked the numbers A and B, plugged them in here. Yes, sir. Or yes, ma'am. Excuse me. It'll always be positive. Well, that's the. Technically that's what we're squaring, though. That's why I'm putting it in there. So when you get done with this, you'll get the square root of 34, right? We'll leave it in that form. So the absolute value, unless it can be simplified, like square root of 45, you could simplify to 3 square root of 5, couldn't you? Like 9 times 5. Anytime you can simplify a radical, that's automatic. It's something I would take points off if you don't do on anything. All right. I don't think we need to do another one of those. That's easy, isn't it? All right, look at example 3. Graphing, you'll notice this is on the same page here at the bottom. We've renamed the axis. Instead of x and y, we've got imaginary and real. But it's treated the same way as x and y. Do you remember which part is the real part in your complex numbers we were just talking about? Let's graph this one. So this is the real part, isn't it? This is the imaginary. This is how easy this is. That's just like graphing that. So since this is the real, we go right 3 on the real, down 5 for the imaginary part. And actually what you found, when you found the absolute value of that same one, was the length of that. Like the absolute value is actually the same thing as the length of this. And here's, you'll see why. Don't we have a rectangle, or excuse me, a triangle here? Left 3, down 5, don't we? And remember, you do x squared plus y squared equals r squared. Same thing. Also, we do the Pythagorean theorem, which was a squared plus b squared equals the hypotenuse c squared. It's all the same thing. So when you graph this, you graph the point and just draw the line to it. All right, turn the paper over. Now, this is how you change a complex number to polar form. In polar form, it equals this. R cosine theta plus I. This is very important that people forget to put in when they're doing this. They forget to put the I in there. But this is the polar form of a complex number. Now, you already know how to find R and theta. We've been doing it for a month now. How do we find r? Square root, that's exactly right. Wasn't r square root of x squared plus y squared? And this time x and y are like the a and b, aren't they? Well, let's do the first one here. Negative 3 plus 4i. So we need r and we need theta. Let's figure out the other part too, how we do it before we do the problem. How have we been finding theta for all year on every problem? Thank you. Tangent inverse. And we usually put y over x, don't we? Well, this time, guess what you're going to put? How about b over a? Because didn't we just graph it like x and y, a comma b, x comma y? Okay. So if I want to find the r, we got the square root of negative 3 squared plus 4 squared, don't we? This one comes out nicely. What is it going to be? 5. Now all we need is theta. Plug it in there and we have it in polar form. Tangent inverse. Now do you remember, we don't worry about the negative. We figure out our reference angle, and didn't we just graph a complex number a while ago? What quadrant's this one going to be in? Second, yeah, because it's negative positive. So first, just find your reference angle, and you probably don't have a calculator because always have to give out 10 of them. So we got tangent inverse of 4/3, which is? Okay, thank you. 53 degrees. And that could be our answer if we were in the first quadrant, right? But we're not. We're in the second. Thank you. So that means we would do this. Your 53 would be in the second quadrant, and we want that one, which is 127 because you subtract from 180. Now we can write the polar form. Don't forget the I. And that's how you write a complex number in polar form. We're not solving, honey. We're just changing it from complex to polar. All right, do the next one for bonus, please. Oh, wait a minute. Got to give you a hint on it. Because this is an example of one that is a special triangle, which means you can't use your calculator on this one. It's got to be in terms of pi, and you got to use your special triangle to get your theta in terms of pi. Go ahead and try this one. Okay. So we have 1 plus square root of 3i, don't we? We want to change that to polar form. And we need to use a special triangle. How can I tell immediately that this one is going to be a special triangle? And 1. Aren't those two sides of a special triangle? That's how you know. That's why you should use it. Okay. Anybody got R yet? 2. Very good. Because we got 1 squared, and whenever you square a square root, of course I still have some people wanting to put 9 there. But what happens when you square a square root? Yeah, it'll just be 3, won't it? So this is the square root of 4, so that's how we got R equals 2. Now do tangent inverse, which was just, all tangent inverse means is find the angle that would give you square root of 3 over 1. Because isn't that what we do? We put this over this, and we want the tangent inverse. That just means find the angle that gives me that. Now, How do we go about thinking that through? Draw something. All right. Molly, we were thinking the same thing. This is 60. This is 30. How do we label our triangle? Yes. Well, if we're doing tangent, aren't we doing opposite over adjacent? Well, then what's square root of 3 opposite of? There's your reference angle. But I want it in terms of pi when we do this. Oh. Come on now. Y'all know what it is. Y'all know what it be. Thank you. See, I told you. See, everybody, 4 or 5 people said pi over 3. How many times does 60 go into 180? There it is, pi over 3. That's how you find it. Now, how do I know that pi over 3 is the answer that we want to use? Because, very good, man. We're in the first quadrant because it's plus plus, right? So, this would be pi over 3. Now we can write it and we're finished.
Did you use pi in terms of pi to the second time?
Yes, ma'am. And now, if we were doing it in degrees, you'd put 60. Same thing. Don't forget the I. All right. Where are we? If you had that done before I did, yes.
What about the R?
I'll give you 1 for the R. Did anybody have the pi over 3 before I did? Give you 1 for that too. 2 total. Beg your pardon? Because this is opposite the 60. See, tangent is opposite over adjacent. Right? We need to find the angle that the square root of 3 is opposite of. And then I just changed 60 degrees to terms of pi. How many times does 60 go into 180? And then that's your pi over 3. All right. Last thing, and then we're done. All right, here we go. Well, whatever we don't get finished, I can finish tomorrow. Cosine of, is this 11 pi?
Yeah.
So we have 11 pi over 12. 6, sorry. Plus I sine 11 pi over 6. Well, to graph this, don't you need an r comma theta? Isn't that how we graph polar points? Remember that? So we already got our r and theta. 4 comma 11 pi over 6. Go ahead and graph it. And this our r and our theta is that, right? Just pull it out. Comes right out of there. Go ahead and graph that on your circular graph there, your polar graph. I don't have that up here anymore, do I? So when you do, don't we have our 11 pi over 6 about here? In fact, I think I labeled it for you, didn't I? On the graph. And then how far out do we go? Yeah, the circles go out to about the end of it here, doesn't it? So that's basically where you're going to be on your graph. How many got that right? Because we've done that before. 1 bonus point. One more thing to show you with this tomorrow. Okay, we have one more thing to do here. We need to write this complex number that's in polar form, change it to rectangular. This is really not that hard. All we do is work inside first and find the cosine of 11 pi over 6. Well, 11 pi over 6 is 30 degrees here. Now, the reason we know that, 6 goes into excuse me, 180 30 times, so that gives us 11 pi over 6 puts us in the fourth quadrant. 30 is our reference angle. So we have square root of 3 here, -1 here, and 2. So cosine is going to be adjacent over hypotenuse, square root of 3 over 2, since we're done 30. And then sine will be -1/2, and then we have our I. Now after we've done that, all we have to do is one more thing, and we've got it in rectangular form. Distribute the 4, and we'll end up with 2 square root of 3 over, just 2 square root of 3. Since the 2 goes into the 4 twice, minus 2i. And now we've changed a complex number that's in polar form to rectangular.